We present GaVS 3D grounded full-frame video stabilization via temporally consistent local reconstruction and rendering. Given an unstable monocular video, we introduce a novel Euro-free video stabilization method by reformulating the task as 3D local reconstruction and rendering. Our approach reconstructs the local scene from unstable input views and subsequently renders stabilized frames based on smooth camera poses. Compared to previous approaches, our method demonstrates remarkable robustness against diverse and intense camera motions while preserving full-frame synthesis and ensuring high geometric consistency. In video stabilization task, unstable and stabilized frames only differ slightly, making it unnecessary to globally reconstruct the scene. Therefore, we omit conventional global optimization and propose to model the scene with a neural network that predicts local reconstructions in a feed-forward manner. Given unstable videos with unstable poses marked in red and stabilized poses marked in blue, we predict localized reconstructions from each unstable view and render stabilized frames on the corresponding stable views. The reconstruction and rendering processes are iteratively performed in multiple rounds, progressively generating stabilized video frames. The feed-forward reconstruction is achieved by enhancing monocular depth estimators with additional heads that predict per-pixel Gaussian primitives. To address the limited generalization and temporal inconsistency of pre-trained reconstruction methods, we propose a lightweight test time optimization. Technically, for each local reconstruction from an unstable frame, we leverage multi-view supervision from neighboring frames. To deal with dynamic objects that violate epipolar geometry assumption, we incorporate dynamic compensation module to synthesis pseudo-ground truth frames. To further improve reconstruction consistency across frames, we treat per-pixel Gaussian reconstruction as multi-channel feature maps and regularize them on dense correspondence on the windows with increased dilation. Furthermore, we extrapolate each local reconstruction with video completion module, providing sufficient coverage to render a full field of view at the stable poses. We repurpose the Euro-based video stabilization dataset in for our 3D grounded task, focusing on samples that cover a wide range of camera motions and scene content, including mild movements, dynamic objects, and intense motions. Our method comprehensively outperforms the baseline approaches in all three scenarios, particularly in intense motion and dynamic scenes, demonstrating superior performance. Meanwhile, the user study indicates that our method achieves leading advantage over other approaches. Compared to cropping-based methods, our approach avoids excessive cropping while maintaining a high level of geometric consistency. Compared to 2.5D methods, our approach better models dynamic objects, preventing distortions at the boundaries between dynamic and static elements. Additionally, it avoids geometric distortions caused by errors in 2D optical flow. Compared to warping-based full-frame methods, our approach demonstrates higher stability in intense motion scenarios and better geometric consistency at the boundary. In intense scenes and scenarios involving camera yaw and pitch rotations, interpolation-based methods fail to model complex camera motions, resulting in unstable frames with blurriness and artifacts. In contrast, our method robustly handles complex motion, producing high-quality results. In the ablation study, we demonstrate the effectiveness of our proposed methods in terms of high-fidelity reconstruction, dynamic object quality, and reconstruction consistency. We method also allows customized stability by changing trajectory filter weights. Thanks for your watching.